Of course, I'd like to thank the organizers. It's a beautiful place here. All right, so yes, so I wanted to talk about Liouville structures on cobordisms. So first, let me make sure to define what I mean. So let's say that W is a smooth manifold compact, and its boundary is given as two components. So this is what I'll call a cobordism. So then a Liouville structure on W, so it's an exact symplectic structure. So I'll think of the primitive as being given. So that I want d lambda to be symplectic. And secondly, I want that, so this vector field z lambda, which is defined as being the omega dual to the primitive, I want this Liouville vector field to be inwardly transverse to the negative boundary, and outwardly at the positive boundary. So the standard sort of picture of this is this type of picture, and then so my z lambda is something like this. So an example of this might be like a I take an affine variety, and I take a big ball minus a small ball in the intersection. All right. So then the theorem that I want to discuss today, which is joint work with Ellie Ashberg. Most everything today is joint work with Yasha. So let's say let W be a smooth cobordism. And it's sort of a genuine cobordism in the sense that both boundaries are nonempty. And then let's just assume that W has an almost complex structure. So let's say, suppose W has an almost complex structure, say J. So I'm just thinking of this as existing up to homotopy, the actual specific almost complex structure doesn't matter. So then W admits a Liouville structure. which is homotopic to this J. Which, what I mean by that is like, you know, after homotopy, J can be made compatible with this Liouville structure. So, of course, the existence of an almost complex structure is necessary because once it's symplectic, you can always choose an almost complex structure. It's not totally clear what, you know, how necessary these non-empty boundary conditions are, but yes.
Are you assuming anything about dimensions?
No. It works even if W is four-dimensional.
You're not saying anything about what the contact structure on the boundary is. I mean, there is one, but you're not saying anything about what.
Not yet, but those are two great questions to go together. So I'll answer them both at once. So as Dusa mentions, you know, anytime you have a boundary of a Liouville structure, so we always get contact structures on the boundary. Just given by the kernel of the Liouville form. So this is going to be contact precisely because this is transverse. So yes, so what can we say about these contact structures then? So kind of a strengthening of this theorem, I guess. Maybe call it theorem 2 for emphasis. So if the dimension of W is equal to 4, then in fact both boundaries will be overtwisted. And then in higher dimensions, so if I'm in a larger dimensional situation, so then I still will always need my negative boundary to be overtwisted. So but the positive boundary I can choose arbitrarily. So this can be prescribed.
Prescribed in contact structure?
Yes, yes. Yeah. C plus can be prescribed. Yes, yeah. Yeah, thank you. And yeah, so since we have this almost complex structure, or stable almost complex structure at the boundary, that's going to fix that. So once we know it's overtwisted, in fact, these things are going to have to be uniquely determined by this condition. This thing can essentially be anything. So maybe I should say a bit about overtwistedness, since that will be used in the proof.
Two overtwisted structure can hold a credit.
Depending on what you mean by fill. So one boundary will be concave and one will be convex,
Yeah.
but yes, in that. So let's see what to say about overtwistedness. Well, maybe I'll delay that for just a second. And give kind of a remark about this dimension condition. So this higher dimensional situation where I can prescribe the contact structure on the positive boundary, I know that this couldn't possibly be true in 4 dimensions. So and the reason for that, like everything in 4 dimensions, is because of some gauge theory. So the simplest kind of example is, let's say that I just wanted to build a contact structure or a Liouville structure on the manifold S3 cross I. And I wanted down here this to be some overtwisted contact structure, the overtwisted contact structure in the standard class. And I wanted on the top to just be the standard contact structure. So this thing cannot be Liouville. And why is that? Let me maybe go over here. So the point is that if I look in gauge theory, you can do this in ECH or in, say, monopole, floor homology. I'm not sure it's possible to do this in Heegard floor homology. Interestingly, but in any case, so I have the monopole floor homology of S3, and this is mapped to itself, and this is by the cobordism map given by S3 cross I. Now, of course, since it's the trivial cobordism, that means it's just the identity map, right? So this is the identity map. Now maybe I should label that with the orientations, I should be going from the top to the bottom. But now, the way this kind of interplays with contact geometry is I have some contact element defined by the contact structure, which is an element of this group. And similarly, there's a contact element here. But what we know about this contact element is that it can never be 0 if I'm looking at some fillable contact manifold, like the standard sphere. Whereas for overtwisted manifolds, it's always equal to 0. So we know that this kind of association of this contact element, it cannot be functorial. But I want to emphasize the reason it can't be functorial is sort of subtle compared to the opposite direction. So if I flipped this, it would be kind of for a very obvious reason that 0 can't be sent to something non-zero, right? This is subtler than that because this is saying that, something non-zero cannot go to something 0. But of course, that's not true in general. I need to know information about this map, namely the topology, the actual smooth topology, is giving me information about this that kind of wouldn't just be picked up by the more symplectic invariants. And then, so the only thing to note is that that if it were Liouville, this would imply functoriality. And so this thing cannot be Liouville. All right, so what else to talk about? So maybe I'll give a couple applications of this theorem. So notice that I'm talking just about exact cobordisms, but I can also give non-exact cobordisms. So the theorem implies existence of non-exact symplectic cobordisms. And this is just kind of immediate, so all I need to do is, so I can just pick some 2 form on W, which is identically 0 on the boundary, and is closed. So, and the homology class is just whatever homology class I want it to be. So then, of course, if I just define omega to be c d lambda plus sigma for some very large c, well, being symplectic is an open condition on closed forms, right? And so this thing will remain symplectic if C is large enough, and it's not affecting the boundary at all, so it'll be the same contact structures. Just kind of this class is prescribed arbitrarily.
Proving exactly, I mean, you need to assume that H2 is not trivial.
Well, yeah, but if H2 is trivial, then I'm not sure what a non-exact cobordism even should be.
So you're saying that under the assumptions of your original theorem, if H2 is not 0, then you can get a non-exact symplectic cobordism also?
Yeah. Or more generally, I'm saying whatever class in H2 you have, you can realize that specific class as the homology class of omega, like 0 or not. Right. So another application is to closed manifolds, or not. So the case where the boundary actually is empty, and let's say here I want my dimension to be strictly larger than 4. So let's assume that that there exists some hypersurface M inside of W. Well, actually, let me phrase it a different way. So let's assume that this is 0. So then if I have any closed symplectic manifold, W connects some M has a symplectic structure. And so here I have only concave boundary. So this is again just sort of an immediate kind of brainless application, but so the proof of this, all I need to do is look at W minus a ball, and then define the positive boundary of this thing to be just this sphere. So now apply the theorem. And now since I'm in high dimensions, I get to prescribe this contact structure, right? So I'm going to prescribe it with to be the standard sphere. And now, well, I can think of the standard sphere as being just the boundary of a Darboux chart. So now if I just, you know, look at M minus a disk where this is an actual Darboux chart. So this has a concave boundary, which is the standard sphere, and so I can glue along this sphere, which is exactly my connect sum. So of course here I'm going to need that the concave boundary is still overtwisted, as the theorem says. So this is kind of a proof that overtwisted manifolds admit symplectic caps, but it's a little bit stronger than that because I can almost prescribe the topology of the cap. You know, not quite, because I may have to connect some this other thing, but it's kind of nearly to that. All right. So are there any questions about the sort of statements or setup for this sort of thing? Yes.
When you had a surgery given by a Morse function on generic Morse function on a symplectic manifold.
That's a great question. So, well, this is essentially the entire proof, right? Because, you know, I can always put a Morse function on the smooth manifold W, and so then all I have to do is just construct like the elementary cobordism for each critical point. So I just have to construct like a model in for every index and dimension. So yes, so we will see this. Other questions before I kind of jump into the more proofy bits? Okay, great. So let me do just maybe a bit of review of some overtwisted type things, what kind of properties these satisfy. So. So first of all, let's give a definition. So so I'll say a three-manifold is overtwisted if it contains up to contactomorphism this standard model, which is just given by, well, what it's given by. So this is just some model, but it doesn't really even matter so much what it is. But the important thing is that it's defined by containment. So if I have some contact manifold and I don't understand anything about it sort of globally, but I have this one picture, then it's overtwisted. So it's sort of semi-local in that way. And then I'll say that a 2n plus 1 manifold is overtwisted if it contains just a product neighborhood of this model. So this is like this is just this form right here. And then plus, say, lambda, where lambda is just equal to the standard Liouville form on C n minus 1, so the sum of xi dyi minus yi dxi. So this ball is in Cn. And so what I want is I want it to contain this for all radii r. Now again, it's really not so important what the specific model is. The only point is that, again, it's defined by some containment. That's maybe not entirely obvious for the definition, since I got this for every R here. It turns out I only need sufficiently large R with some constant that depends only on dimension. But since I don't know what that constant is, let's maybe phrase it this way. Right, and then so the main theorem concerning overtwisted manifolds, which, well, in the 3D case is due to Ellie Ashberg, and in the higher dimensional case is due to Strom-Borman and Yasha and I. Which says that, well, so I'll maybe give two important properties that I'm going to use. So first of all, I want that if I have two overtwisted contact structures, on a manifold M, and let's say that they're homotopic as, let's say, stable almost complex structures. Then, in fact, they're isotopic. And a statement that essentially kind of follows with this one together with an existence theorem we proved is that overtwisted manifolds are universal embedding spaces for contact geometry. So so let's say I have a containment, let's say I have an embedding of one contact manifold into another, but this is only a smooth embedding, so it's not a contactomorphism. Okay. Let's even say that this is codimension 0, because that's the only thing I'll really need. So then let's assume that, let's maybe give this inclusion a name, maybe iota. So if the so if this map is just a map which gives isomorphic, stable, almost complex structures, so that's some just obstruction theory calculation. So assuming this is true, so then I is isotopic to a contact embedding. And in fact, we can even get a little bit more. So I need that this is overtwisted. I'm not stating that here, I guess, but I certainly need that. And I can also get that that M minus this new embedding of U. So say iota tilde. That even the complement is overtwisted. So
You do want to assume that this complement is
yes. It is true in all dimensions, yes. Yeah. So here, let's say just U is open and it's the same dimensions. All right. So yes, so this is essentially saying that, like, as long as it's just vaguely possible for me to embed a contact manifold, if the target space is overtwisted, then it is actually possible. All right. So I set up all of this fancy new high-dimensional stuff, but maybe I'll just discuss, or at least start by discussing the proof in dimension 4, because it's a bit easier. So proof in dimension 4, proof, of the main theorem. Not this theorem, definitely not.
Is the proof entirely at H principle?
What does that mean?
Whatever you wish to think about.
I mean, yeah, it's certainly an H principle style.
It looks like.
Yes. So I would say it's somehow still not ideal because we still don't know how this positive condition at the boundary, that being non-empty, if that affects anything. Also, we don't have anything like a parametric theorem. So if we're given, say, the topology and the almost complex structure and the contact manifolds at the boundary, I don't know if our construction is unique, which is a great question, but I don't have any idea how to solve that one. Okay, great. Other questions about? Okay, so now here we are at this 4-dimensional proof. And so it suffices to build by handles, right? So the only thing I need is index equal to 1, 2, and 3. Since I have non-empty boundaries, there's no mins, no maxes. Furthermore, if the index is equal to 1 or 2, well, then I can just use Weinstein handles. So this is sort of a classical-ish thing. If you're not familiar, yeah, let's just say that it's very well understood. And in general, up to half dimension, there's kind of no problem with this. So now if index equals 3. So this is kind of the interesting part. So my strategy then is I want to take this kind of model smooth index 3 handle and I want to cut it apart in such a way that well, to kind of make large pieces of it have a half-dimensional homotopy type. So what I'll do, so I can think of this as, maybe just being 2 S3s, and down here just being like S1 cross S2. I mean, that's not, well, maybe let me not write that because it's more relative than this, but so think of this as something with corners, maybe. But so what's the main problem with the 3 handle? Well, it's going to, locally to the handle, it's going to have this disconnected boundary, right? So this is kind of the first problem. So what I'm going to do is I'm going to just take a cylinder and join these. So I'm going to embed just S1 cross I, where the interval portion actually connects to the boundary. And I like this because, well, if you stare at it for a little bit, so let's maybe call this original thing W, since this is all I care about. And let's call this thing sigma, this 2-dimensional surface. So then the claim is that if I look at the complement of this surface relative to the original negative boundary, which hasn't changed at all, this surface doesn't intersect the negative boundary, that this has half-dimensional homotopy type. So what's the basic reason for why this is true? So instead of S1 cross I, let's imagine that I did like a full D2 cross I. So then I'm just like deleting the co-core itself, right? Well, if I delete the co-core, then this thing has no topology at all. It's just a trivial product. I'm just undoing the surgery. Well, so I'm not quite doing that. I'm, instead of doing D2 cross I, I'm kind of drilling out the middle of this. But if you think about it, what do I need to add to kind of drill out the middle of this kind of origin cross I in the disk cross I? Well, that's exactly a 2 handle. So I can be totally explicit here and even say that this is just, it's just a 2 handle. So that's good because, well, I know how to put a symplectic structure on this because I've reduced it to this case. But now, of course, I need to figure out a Liouville structure near the surface, and I need to do some sort of gluing problem, right? Okay, where do I want to go? So by sigma, I mean just the cylinder itself. Sorry, say that again.
Are you still left with the interior of the cylinder inside
yes, absolutely. I mean, it doesn't separate since it's a surface in a four manifold, but yeah. So now, an extremely important part to this is that now if I take like a neighborhood of sigma and I think about the boundary of that, well, I'm thinking of that as like positive boundary, right? So when I glue my Liouville structures, they're going to have to sort of match this, right? So now here's how to do it. So, so first, let's just let lambda, well, I kind of used lambda before. Let's let beta be a Liouville structure on sigma itself. So it's a cylinder and it's a Liouville structure. Well, I mean that it should have concave boundary on, both sides. Sorry, convex boundary on both sides. Now I can find an embedding of boundary sigma inside of del plus W with its contact structure, which is assumed to be overtwisted. Okay, great. And then I can even say that the neighborhood, I can say that my contact structure, well, it's going to be the kernel of just beta plus r squared dt, where this is just like polar coordinates on C. So this is just a standard neighborhood theorem. So this is sort of bad because if I look at beta plus r squared dt, the Liouville vector field is like radial on C, right? So instead, what I'm going to do is I'm going to define so near sigma, I'm going to define mu to be just beta plus r squared minus 1 dt. And notice that this is actually singular at r equals 0, right? Since these are polar coordinates. But that's maybe okay because, well, at least d mu is still defined everywhere, right? Because d mu is the same as d mu plus d dt, which is actually defined. But see, if I look at my z mu, well, if I just do a bit of a calculation, this is the same thing as just z beta plus, and I think it's r plus 1 over r del r. And so this is something that's flowing inwards, but it doesn't get to a sink. It has a pull at the origin, right? Okay, so great. So now I have this contact form. Now notice that by my definition here, sigma is null homologous because, again, I have this d2 cross I. So I can assume that that dt actually extends to all of W to W minus sigma as a closed one form. Should I give it a name? Yeah, let's maybe call it theta. So I can just extend it because it's null homologous, and dt is like defining the dual of the neighborhood of the boundary of sigma. Okay, and now what's next? Oh, and let's also assume, which of course I can do, that theta is just 0 on the negative boundary, which, the negative boundary isn't interacting with the homology at all of this divisor, so that's easy to do by adding something exact. All right, so now I can extend mu to a neighborhood of W plus as just mu equals alpha minus theta. And we see that this agrees with the mu defined here. If, oh, sorry, I haven't defined alpha. Alpha is my contact form on the original overtwisted manifold. And furthermore, because I can choose alpha to be large, right? I mean, we're kind of constantly using this argument of making things large to keep this contact condition. So I can say that mu is still contact on this positive boundary. And I can, if this isn't true, I can just replace alpha with some large multiple. Okay. So now let's maybe draw a schematic for what my W looks like. So it looks something like this. So I have like my sigma here. This is my positive side of W and my negative side of W. And then, so my Liouville form is, or my Liouville vector field is pointing inwards towards the divisor. And since this is still contact, with the same sign, then it's also going to be pointing outward through the positive boundary of W, right? And now, well, everything that's left has half-dimensional homotopy type. So I can...
Sorry, I missed maybe the main statement. What is, to which extent is this Liouville vector field unique?
I mean, it's Z mu, as I've defined mu here, kind of on these two separate pieces. So yes. So I mean, the essential idea is like if I just took b plus r squared dt, this near sigma, this would be expanding. So this is kind of bad. So I'm going to subtract dt, which makes it singular, but now it's inward pointing, which is good. Now I want to match this with the contact boundary that I already have given to me. So I just subtract this dt from the alpha as well, and so everything glues smoothly. Right? Great. Any other questions? And so now the punchline is here. So now if I just build a Weinstein structure on this W minus a neighborhood of sigma, where I should say that my positive boundary with the positive boundary is given not by alpha but by mu. So there's a little something to say here, which is, why can I build this Weinstein structure? Because I'm starting from the positive end and I'm moving down, right? So that's usually something that's hard to do because it's like a coisotropic surgeries. I mean, it's Weinstein surgeries, but it's coisotropic surgeries. So that may be hard to find coisotropics. In general, finding coisotropics is hard. But I'm overtwisted, and I got my number 2 here. And so it's easy to find coisotropics in order to build this cobordism. Since the complement is always overtwisted, that means I'm going to be overtwisted at the bottom. And so the the contact structure induced on boundary minus is going to be overtwisted by construction. Now, this still isn't good because it's still singular at sigma, right? But now, so at the very end, I'm going to define lambda to be just mu plus theta. And the key observation here is that theta is closed. So if I started with something which is an exact symplectic structure, and I add something closed, well, that certainly doesn't change if it's symplectic. Now, being Liouville, I need to be symplectic and also have this transversality at the boundary. But that's just a condition at the boundary. On the interior, I don't care at all what happens to the Liouville form because it's closed, and so d of it doesn't change, as we noted here. And at the boundary, well, I control everything because at w plus, I'm just getting back to alpha, and at w minus, well, I haven't changed anything because it's 0 there. And so that gives the construction. Maybe I'll just say one word about the higher dimensional case. So first of all, I don't know why I'm pointing up here, the theorem's gone. So first of all, being able to prescribe the contact boundary at the top, that's kind of completely irrelevant to us. So it turns out that in high dimensions, there's always a concordance from an overtwisted contact manifold to any contact structure you want, just on a product. So, and that's theorem of myself with Roger Casals and Fran Presas, which is, kind of a separate result. But so since I have this concordance, I can always just kind of chop that off the top. And even in the high dimensional case, I can work with overtwisted the whole time. And the difficulty in high dimensions is, well, I want to do a dimensional induction. Well, here I started with a cylinder, so that's easy to build something Liouville. But in higher dimensions, I'm going to get something with this singular point where it's undefined. Because I can kind of only construct cobordisms, not actual Liouville manifolds. but there are ways to kind of get around this singularity and to kind of push this around the manifold a bit. Yes, sorry for going over time. Thank you.
Any more questions? We're supposed to use the microphone for them. All right,
I can speak loud. What is the main application of that?
I have no idea. Maybe no application.
So what would be the main, the first obvious application of that result?
I don't know of any that are sort of nicer than the statement itself, I guess. I mean, so it's, of course, kind of starts from wanting to just build symplectic structures on whatever objects we can build symplectic structures on. This is kind of just like the nicest thing we could build a symplectic structure on.
But precisely, no, there is no...
No, not that. I mean, so, I mean, maybe say, for example, that like, you can say that there's a symplectic structure on CP3 minus a point, so that its boundary is an overtwisted S5. So this looks kind of completely different from the usual CP3 minus a point. But that's just sort of an example that can be built. You can just kind of build endless examples of this type, I guess.
This might be a ridiculous question, but does your results give any strategies or examples of existence of symplectic structures on closed manifolds? For which one didn't already know that?
Yeah, no, that's a great question. So the sort of idea, I guess, of, I mean, so by Donaldson's theorem on asymptotically holomorphic sections, any closed symplectic manifolds can be written as a Weinstein manifold together with a neighborhood of the divisor, and the neighborhood of the divisor looks exactly like this, with this R-1 singularity. So, yeah, I mean, one could kind of fantasize about such a proof that would look similar to this. The issue is I don't have any idea how to do the induction since it's false in dimension 4, so that's an issue. The second issue is that we kind of use overtwistedness everywhere to solve this gluing problem. So if we didn't have that, and we can't have that if we're dealing with closed things, then this gluing problem to solve seems difficult.
If you could somehow, if you chose a submanifold dual for your symplectic class, if you could somehow choose J to preserve its tangent bundle, then I guess you could hope to run sort of a dimensional induction construction, but only down to dimension 4 or something.
Yes, yeah. But yes. But so even aside from that, I mean, let's assume somehow we get around this dimension 4 by choosing some crazy hypersurface that we do know is symplectic. The gluing problem exists, but so what I'm trying to do is I'm trying to find a concordance between pre-quantizations and boundaries of flexible Weinstein domains. And that gluing problem, which we would have to solve by concordance if we want to fix the topology, I don't know at all how to construct such things.
let's thank Emmy again and go to lunch.